All right, hello everyone. So today I'll be going over my current work in progress, and we worked on a complexity-based convolutional neural network, and for the purpose of malware classification. So this is a work with me and my supervisor, Professor Ken Ferens at the University of Manitoba, and this work was presented at CSCI 2020, December 16th in Las Vegas, Nevada. So presentation overview, we'll go over the problem, some general background related to malware, some machine learning techniques and how those are approached. Secondly, the methodology and the novel aspect that we add. Thirdly, the results, and fourth, the conclusions of our work. So overview. In terms of malware detection, it's an ongoing issue for antivirus vendors and researchers alike. And the reason why it is because it's a constantly changing dynamic field of research. Malware, as it exists currently and as it's written by various writers, every single time it's deployed to a new environment, it has self-encrypted payloads that are able to encrypt itself and obfuscate through a series of packers and other techniques. So currently, all malware observed today, about 93%, is polymorphic, meaning it changes upon iteration to iteration. And the reason why this is a problem is because legacy techniques, which tend to be more signature static based, they're unable to adapt to new zero-day attacks. So every single time a malware is deployed, previous systems are unable to classify them because it's something that it's never seen before. So it either changed itself ever so slightly to avoid obfuscation, or it's a new attack entirely. And when you're looking for a certain set of signatures, you'll never be able to find new signatures because that doesn't exist in your table. Thirdly, malware analysis can be separated into two approaches: static and dynamic analysis. So static features, if you were to use one sentence to distinguish static from dynamic, static are all features that can be retrieved from malware before it's executed on a host computer. So anything that can be disassembled or looking even at the file structure is considered static. So that would be things related to the control flow graph, importing API libraries, opcode and opcode frequency and n-grams, and the file entropy levels. Dynamic features are all the sorts of features that can be retrieved after the malware is executed on the host computer. So it would be anything related to the amount of system resources it uses, the process and the spawn behavior of its sister-daughter processes, network activity, and things like file system, whether it creates files and deletes them, registry, anything to do with sort of the dynamic nature of how it tries to gain root access on a host computer and then make contact with a command and control system. So when these static or dynamic features are retrieved, machine learning practitioners use a combination of heuristics and hybridization in order to take all that information and either organize it in a certain way or grab only the useful features and then import that into some sort of machine learning environment where we can perform classification and prediction. So just as an overview of static methods, because that'll be a focus of what we do in this work. Static methods have a unique fingerprint of the malware. So you can, because it's all the information that's contained within the malicious file before it's executed, you can sort of think of it as a fingerprint, right? So how does it look? So things like API calls and the control flow graph, you can imagine that each malware has a unique fingerprint. The problem is that it can be easily fooled through obfuscation and anti-armoring techniques. Like I said, if you're looking for certain signatures, all it takes is for you to change the way you look ever so slightly to avoid that detection. If you have signatures that are too broad, well, it may be the case that it will flag benignware. And if they're too specific, then you won't be able to adapt to those new forms of obfuscation because what you're looking for is too specific. And secondly, anti-armoring is of consideration. That is malware that once it's executed actually looks for a virtual environment. So it can look if it's being run on in a virtual environment with let's just say a virtual network card, and it can look for certain things related to maybe a hard drive serial number, and it'll know it's not being executed in a real environment and won't execute at all. Or what it'll do, it'll execute a set of garbage code instructions so that the malware researcher and that's carrying out the disassembly will be overcome with garbage instructions. And secondly, also things like entry point obfuscation, which is in the malicious binary, where exactly is the malicious payload being put into the memory stack, right? At some point, through a series of pointers, it's the malware through its control will point to the payload, but the point is where exactly is that entry point, and it's obfuscated by using a series of jump statements, or it's just randomly, which with each iteration randomly put an assortment of the file body. Thirdly, signature-based techniques need to be robust and generalizable. So in the previous slide I was mentioning, and a little bit in this slide, about specificity. We can be too specific, but we can also be too generalizable, right? So there's that balance. So here at the bottom I have an example where you have a large number of false negatives when you're too specific. Because again, you're looking only for a certain set of signatures, and slight modifications to the obfuscation will fool your techniques. And then of course you have false positives if you have poor generalization. So you have to be able to generalize to those new and emerging threats. And shown on the right here is just an example of two malware binaries, each of which belongs to the same malware family. Upon just an initial look, you can see how there's similarities, but at the same time, large sections at the bottom look different. So visually we can see that, but whether or not a system can do that dynamically online, in an online format, is another thing entirely. And how are these malware belong to this family and not other is again another consideration. So the problem statement is we want to look at novel techniques to improve our own detection and classification of malware, and we want to do so just simply looking at the binaries. And this is a very powerful technique because, rather than going through the disassembly process, if we can just look at the malicious binaries, we can have an idea that there are pertinent differences and similarities between some families and not others, and that just speaks to how powerful all techniques are. And secondly, we want to create a more holistic fingerprint which reflects each individual section of a PE, port executable. So on the very right here, we have A, B, and C. C is an example of if we were to section off in very general terms that malware binary, exactly where those PE sections would be. Again, just very generalizable, right? And there's more, but this is just for visualization purposes. So if we wanted to have a fingerprint, we need to know a fingerprint of certain sections of the malware binary and how they change or how they're similar between malware families, within malware families and between malware families. So it's a more holistic fingerprint. We're not just taking the fingerprint of the whole thing, we're taking sections of a fingerprint. And additionally, we want to improve the specificity because we want to distinguish one malware family from the next and variants within those families. So between A and B, we can see that visually there's distinct differences, but these are just two examples of thousands. So at what point is it distinguishable from one family to a next, and at what point are they similar? And that's what we want to look at. So methodology, one of the ways that we aim to improve that specificity is by extracting salient features from these PE sections separately, and we use something called complexity analysis. So complexity analysis is the idea that things behave and act in a self-similar fashion, and that there's a relationship between taking successive measurements at different scales. So at the top right here, we have three separate squares, each of which actually has the same image, but the resolution at which we're looking at the image changes from 1, 2, and 3. So n sub k corresponds to the scale that we're looking at. So n sub k1 means that the whole image is the scale that we're looking at. N sub k equals 1/2 means we're cutting up the image in half portions, and n sub k 1/4 is that we partition everything into 4 pieces, 4 by 4. Right, and capital N sub k is how many times within that scale that we're looking at the object appears. So in the first image, the black images, black blots, let's just say those smaller black squares, only actually appear once if we're just considering the whole image itself, that whole square. But in the next, in the second square, n sub k or capital N sub k is 2, and that's because if you partition it into 4, those black boxes actually only appear on 2 out of 4 of those sections, and at capital N sub k, you can see that there's exactly 4 squares in all 16 of those sections. So if we were actually take a relationship of the log-log plot between 1 over the resolution that you're looking at, and on the other side of the log plot, the number of occurrences in that measurement, what you'll see is that there's a linear relationship. And one of the benefits of using this is that it's a very powerful technique, even for very complicated images like a malicious binary, and it can be computed very quickly during the feed-forward propagation and for prediction, of course. And that's very important because our techniques need to be online for that reason. And it's perfect for analyzing binaries because it actually, I like to say, it extracts the context of the information. So everything might not be perfectly log-log plots where everything is perfectly linear, but it may be the case that some sections do follow certain relationships more so than others. So you actually, because of that relationship of scale, you're actually getting more of a contextual information of what you're looking at. And when it's recorded, we record that as something called the fractal dimension. So methodology, it's not just a matter of the complexity that we incorporated. We actually wanted to take an existing architecture and modify it so that it can be used for complexity analysis. So this technique is called the Complexity Convolutional Neural Network, or XCNN, and it's something where we implemented directly into an existing convolutional neural network architecture. And there's a series of improvements that we made. One being the parallelized vel-max pooling acts as a built-in vel size covering. So shown in the image at the bottom, those green squares are actually parallelized vel-max pooling layers, and each one of them corresponds to a certain resolution of analysis. So one could be a 1x1 box, the next one could be a 2x2 box, which acts as a kernel, and then the next can be a 3x3. So it's actually performing the vel-max pooling, but it's doubling as complexity for the purpose of complexity analysis. And then we have 2 other sections: tensor summation, complexity vectorization. So tensor summation is just to say that the information that we're interested in developing max pooling is the occurrence of a 1 versus a 0 in the malicious binary. So we need to sum it over a series of columns over certain axes. And then the complexity vectorization is just us actually performing the computation. Again, so that's just the log-log plot built into the convolutional neural network. So we use that to compute the fractal dimension in the forward pass. And the third thing that we added was the idea of the expanded batch size to preserve the PE section. So in the typical CNN architecture, you have height, length, and you have the number of channels, which are typically color channels. So in our implementation, we don't have color channels, but what we did was we partitioned the malicious binary into subsections. So each of those are sort of the third axis, right? The third dimension tensor, and we just stacked it that way. So each expanded batch dimension is actually just the malicious binary, just cut them up into sections. And with all of this, we feed this into machine learning frameworks, perform softmax classification in order to carry out categorical classification. So this is just a visual look of how these convolutions are carried out. Again, what we are in fact doing is we're not typically doing 3D convolutions on a 3D tensor as you would typically see in literature, because we don't care about that information between color channels like a typical filter would. So what we're in fact doing is we're taking 2D convolutions over a 3D batch size. So the input and output has the same third dimensions, so n sub c, n sub d. Those have the same dimensions because the 2D convolutions are just getting that information from each layer, and then it's doing so for each of the extended batch dimensions, and it's not convoluting over that third dimension. So in this way, we're performing 2D convolutions over the 3D batch size. Again, we're not working with color channels. And additionally, the vel-max pooling layer has to work the same way, where you're taking the vel-max pooling and you're not max pooling in the third dimension, right? So those dimensions remain consistent in that third third layer, third axis. So with the data set, we wanted to work with a representative data set that was also commonly used in literature for comparison's sake. So we looked at a data set with over 9,300 malicious binaries, all contained from 25 separate families. So one thing to note about the table on the right, which is just the family name, type of virus family that it belongs to and the number of variants in the data set, is that some classes are significantly underrepresented or overrepresented compared to others, right? So the Elapole worm family has over 3,000 variants in the data set, while some samples such as skin trim only have 80. So for that reason, we use the corrected weighted matrix. That way, during training, we don't end up with 99% accuracy because our model just loves caring about those overrepresentative data samples. We need to show it's representative for those rare binaries. So we use a weighted matrix in order to take care of that. And you'll see in our confusion matrix that is taken into account. And for comparison's sake, we imported models, award-winning models, the Inception v3, VGGNet, and ResNet architectures, all used for general image classification tasks. And these are extremely sophisticated models with parameters ranging from 23 to 138 million parameters. So these are very dense, complicated architectures. And for good reason, they're used for general image classification tasks. Just for comparison's sake, our own model, depending on the kernel size of the convolution, and of course the number of convolutions, we only have 190, give or take, total parameters to be concerned with. So our results of a confusion matrix is that the convolutional neural network performs categorically at 96.54% accuracy on the Malenge data set. So here we have the confusion matrix of the predicted and true labels. So one thing to note is that certain malware families have significant issues with recall and precision. So false positives are noted for the Swizzer and C2LOP families, where specifically for the Swizzer families, we have classifications of false positive rates, and give or take 0.6 or something like that. So that means 0.4 are incorrectly classified as the other families. Another thing to note is that C2LOP in particular, again, those are the only troublesome families that we've noted between two families, the C2LOP and Swizzer. But one other thing to note is that we had poor classification with one particular malware family, the Malex Gen J family. So about 50% of the time, give or take, it was correctly classified as a Elapole when it should have been Malex. So these families, just to note, have significant structure similarities. Not only do they belong to the same family, but as we show in the next slide, significant issues even amongst literature and other models in classifying these particular families. So these lead to high false positive, false negative rates. And according to literature, these families are the most difficult to classify. So if we were just to look at, in the table to the left, the C2LOP and the Malex families, our model, along with others, have difficulty in terms of precision recall and F1 score. So we show that, give or take, we have some improvements over the other models, and in other cases, we do worse. But the only thing that is a real exception to other models is that our classification of Malex Gen J is actually, other models don't have issues with classification, but our model evidently did have. So that sort of speaks to maybe a fault in the form of classification, because if the complexity classification performs so well in other models, what is it about this particular virus generation family that gives our model more troubles than others? So that's something worth pursuing and worth looking at. And just in terms of total accuracy, one of the things that we did, as previously said, was we looked at our model and compared it to others in literature, and as well as different machine learning frameworks and those imported from elsewhere. So one thing to note was we did outperform a large bulk of other models, but it was outperformed by more sophisticated models, whether it be ResNet, GIST, or Inception v3, and those implementation with a linear support vector machine did outperform our models. So the reference says this work, not that it's our own implementation, but just that we tested it, and that was our results in this experiment. So compared to other machine learning models, our complexity convolutional network did outperform at least just basic performing complexity analysis and importing into a k-nearest neighbor or support vector machine or random forest. So that's one of the other things we want to do was our improvement due to the convolutional neural network architecture itself, or was it just a matter of the complexity analysis being so strong and extract such salient features that that just passing them into a k-nearest neighbor support vector machine is enough for classification. So we did compare those, and we do note that if you shown on the right, the convolutional neural network did outperform the other ones. So one thing to note, and would be a great takeaway, is that we show significant performance with such a relatively simple novel architecture. When you really think about it, it's not sophisticated, but it does what it's supposed to do. And yeah. So just final conclusions. We show that the complexity convolutional network, we were able to implement that within, integrated into a modified CNN architecture, and we implemented several extensions on that with extended batch sizes, deparallelized Velmax pooling, and performing and determining complexity within the feed-forward network. So our model was tested on 9,300 malicious binaries belonging to 25 families, and we were able to perform at 96% plus categorical accuracy. Worthy to note particular difficulties for select malware families, in particular the Malx family. So our model implementation performed comparable, I could say, to state-of-the-art models, and at the same time it had only a fraction of the order of trainable parameters. So that's something important to note, that these are sophisticated models that have been trained on millions of images. This model is extremely quick and can perform at this performance. So with that, I'll take any questions anyone might have in the comment section or by email. Just let me know, and thanks for watching.